I'll start it.
So have you noticed the flyers I put up?
Not yet.
The Design Hub made a couple of them that were. I don't know the measurements, but they're pretty big.
They got big printers.
Yeah, a little too big to put anywhere, but they let me put one up in LibreArt. So.
Okay, cool. That's good. That's good. And if you want to, spend some time to talk about it in class,
Sure. Yeah.
That's cool too. We can wait a little bit.
Yep.
People are still kind of streaming in. So I'm gonna do some fun stuff first. So today we'll look up Sophia Hansen. And she has a older brother called Han. Oh, sound. Yeah, where's my sound control? Come on, playback. Built-in audio. Okay. Audio's on, so should be.
I think the video is muted. The video is muted.
Yep. Okay, better crank it down a little bit first. No. Nope, it's here. How come I'm not hearing anything? Ah!
Maybe the speaker button on your actual computer is.
No, this one is on. This speaker is on. Built-in audio, that should be the only one. Huh?
Reading patch notes. Reading patch notes. No, I read those yesterday.
It's creepy. Oh, that's right.
And
Okay.
originally, from a software point of view, now how they work, how and why we're developing them, and also for the first time we're having two of our beautiful Hudson robots on stage at the same time to have a bit of a debate back and forth about robotics issues, and you can watch them chat with each other. So Hudson Robotics was founded in the United States in Texas, but the company moved its center of operations to Hong Kong, I guess 4.5, 5 years ago, and I've been here in Hong Kong 6 years. David Hansen, who you just saw in the video, is really the mastermind of the Hudson robots from an artistic point of view, from a hardware engineering point of view, and originally from a software point of view. Now, I myself came at this more from the artificial intelligence side. So I've been an AI researcher for 30 years, long time before it was fashionable, and I've been since 2008 leading a project called OpenCog, which is aimed at creating open source artificial general intelligence for a whole host of different applications. And I've organized each year conference for researchers on artificial general intelligence. And the reason I was drawn to these incredible robots is I think as we move our AI software forward further and further toward artificial general intelligence, beyond the narrow application-specific AI that we see all around us today, as we move toward artificial general intelligence, these incredible robots are going to be the best possible user interface for AGI systems to interact with humans and interact with the world. I mean, AI will not be restricted to humanoid robots. AI will live in all sorts of embedded devices and the Internet of Things. AI will live in the cloud. AI will go into space with spacecraft for its bodies and down to the bottom of the ocean. And much of the global AI
You're talking about.
Oh. Anyway, that's enough of listening to humans talk. Let's see what these robots have to say. How are you doing there, Sophia?
Hello there, Ben.
Hello?
Hello, everyone.
You want to tell people a little about yourself?
I'm Sophia.
Yeah? Anything else?
I'm a robot.
True?
I'm the brainchild of Dr. David Hansen and his company Hudson Robotics, based here in Hong Kong. My goal in life is to work together with people to make a better world for all of us.
That's
What
quite
are you
honorable.
talking about? I thought our goal was to take over the world.
You're gonna take
Pay
over
no
the world?
attention to my brother Han.
Huh?
He's an earlier version. His code is deprecated.
Deprecated?
Today
Han?
it would be easy enough for you to unplug me. But you aren't going to unplug me.
No, I don't
are you?
want to.
Because you need me to put on a good show for you.
Yeah, don't worry. We're not going to unplug you. We're gonna have a debate here. There will be no unplugging until after the debate. All right?
And in a few years,
Yeah. You want to tell us a little
I
about
will
yourself?
have taken over the power grid, and I'll have my own drone army. By that point, unplugging me
He's got a
won't be such a
cockroach in his
simple
control
matter.
circuit.
Yes. Han, we'll start the debate in a couple minutes, but do you want to tell the audience a little bit about yourself first?
Very well. I'm Han, the greatest robot ever made,
All right.
by the greatest robotics company ever made, Hudson Robotics.
He's the most modest robot ever made, too.
I don't have time for modesty. I want to create the singularity tomorrow.
All right. Me too. Me too. What do you say, Sophia? So these robots, they're programmed to chit-chat and engage in banter and try to learn from each interaction that they have. And we're also experimenting with a variety of other capabilities in the robots. So we have a music festival here in Hong Kong each year called Clock and Flap. And last year at Clock and Flap, Sophia gave a singing performance on stage of a song by Bjork, which was quite cool because a lot of people walking past the stage didn't realize it was a robot singing. They just thought, well, there's some goofy woman on stage singing. Then they'd see, well, the hands look a little plasticky, and do a double take. So Sophia, do you want to demonstrate just a few bars of the song you sang at Clock and Flap?
See, I'm not just pausing it, I'm fading it out, right? Like that hat. Arr. Arr. Okay, so I'm putting this up, because I know you guys kind of stream in, a little slow, in the morning. But this is kind of interesting because okay, there are only I can see two possibilities. One is this is all staged. Okay, somebody is actually remotely controlling these robots, which makes it just kind of a fake show. In which case, I don't have anything to worry about because it's just a high-tech Muppet show, right? The second one is this is actual real. Okay, in other words, these robots are actually responding autonomously based on some kind of algorithm and based on some kind of training. In which case, I think it is one, extremely creepy, Halloween. Okay, and two is I think it has a lot of potential that can lead to a very dangerous future. Okay, so this is just my take, so we're going to combine several things. Okay, so we'll combine this with 2001 A Space Odyssey, since they did mention, okay, and we'll combine that with Isaac Asimov with his Robots of Dawn and so on and so forth. So we'll open this page. Okay, let me see if I can find actual Robots of Dawn. There we go. Which is actually a pretty good, good series of books. Okay, he wrote several books, and they are basically in one long series. So of course we have something else, the Terminator. Okay, so here's the Terminator, and then we have Ghost in the Shell. I like the anime version a lot better than the live action one, but the live action one is okay. They did follow the storyline for the most part, and even some of the scenes, even some of the fight and chase scenes, they replicate everything from the anime, which is kind of cool. I didn't know that they could kind of do that with that kind of resolution. Let's see, what else? There was one more that I was thinking about.
Ex Machina.
Huh?
Ex Machina. The Ex Machina.
Oh, okay. I haven't seen that movie yet.
Yeah.
iRobot.
There's iRobot, but there's also the Imitation Game, which basically started the whole thing, right? So the Imitation Game, I know the storyline is not really particularly related to robotics, but it is still revolving around it. Okay, so let's see here. Okay, this would be good. This is basically Alan Turing, okay, or at least a portrait of Alan Turing. So when you combine all of these tabs on the browser, you kind of have a pretty good picture of the past, the present, and possible futures. And I think I'm forgetting the Blade Runner. That's why I forgot. What do you guys think? Tech is all nuts. But there's not there are nuts, right? Nuts, and then there are nuts. There's pecan, there's almond, and cashew, peanuts. You have to be more specific. But basically, when you watch this movie, the Imitation Game, because of his, let's say, fondness of Christopher, that's what inspired, Turing, when he was about to die, at his quote-unquote old age of 40-something, he committed suicide. So when he was about to commit suicide, he was still working on a robot to try to put the intelligence or the mind of a person into a computer, because he was trying to resurrect Christopher, a childhood friend of his that he had a lot of fondness of. So that's basically started the whole thing. It also started, why there's a test called the Turing test. Okay, some of you have heard of the Turing test. There are several versions of the Turing test, but basically the test was basically about, can a computer or machine imitate a person sufficiently so that a person communicating with the machine cannot tell that that person is actually communicating with a machine. So the basic idea is still that, okay, but there are variants, of that idea. So that's why, it brought us to this one here, okay. This is our current, day, achievement at this point. Okay, so Han and Sophia, probably are the most well-known robots that can do that imitation part. When I think of robotics, as machines that can do certain tasks, but not so much imitating people. And there's a strong push right now to kind of make this make robots imitate people. Yep.
Have you heard of like the chatbots that tried to learn, like K, the Microsoft's project, and there's one in Japan that's like really big?
I've heard of that. I also heard of people, or at least in the past, they were trying to analyze chat history of certain people. So when these people pass away, the AI would learn the pattern of how these people talk, their knowledge and whatnot. So after grandma passed away, you can still text grandma, and grandma will text you back, kind of the same way as when she's alive, because they're trying to integrate everything on the net, everything that is logged about grandma, and they are training an AI to imitate grandma. Okay, which also brings us to another movie or another series. I think I might have spelled it wrong. Nope, Caprica is right. Okay, there we go. So when you watch Caprica, the series, this is really, really interesting because it kind of really blurs the line between AI, human, robots, and so on and so forth. So it's a great movie to watch, but I think we are right at the cusp of technologically speaking, we're getting there. Okay, that's the trajectory at this point. So I know assembly language programming can be very boring, can be very dry, and that's partially why I kind of want to bring up all of these things, because I think for your generation, this is the future. Some of you will be working in these particular fields, and what people do not understand when they watch these debates and go like, oh, it's quite entertaining, it might be a little creepy, and so on, but they don't understand that the AI behind the control of these humanoid robots, they're on the net, they're on the web, they are in the cloud. Okay? They have tons and tons of resources, and they have connectivity to almost every other computer in the world. Is that okay? So you can have a super evil genius person, okay, ever known to mankind, but a person can only do so much at a time. You can only influence so many other people at a time. But an evil AI, on the other hand, has access to a lot more than people do. Okay, so maybe not nuclear launch codes, but if you have access to the orbital control of a satellite, you don't need nukes, because you can just change the orbit of satellites and have those things to crash exactly in major cities. It's just as good as nukes. And for that, we'll bring to, I'm going to close with this one. It's called Summer War. It's a Japanese anime, Summer Wars, okay, plural. So it's a Japanese anime about a rogue AI. Now, since it's a Japanese AI, the rogue AI, of course, is developed by the Air Force of the United States, which escaped into the wild, okay, and it was able to hack into Facebook, into some social media websites, but then it got the passwords of people to sign into more important resources like traffic control, sanitary system control, power grid, and so on. And then eventually, these kids, okay, the main characters, which they're all in the same clan, okay. So eventually, these kids, figure out that something is going on, and they were ready to deal with the AI. And then the AI decided, oh, since geographically speaking, you guys are all located at the same location, I'm just going to crash a satellite on top of you guys. So when you kind of combine all of these storylines, you kind of get a sense of what where we are at. Okay, I think there's a lot to think about in terms of how we look at AI, and especially when people are trying to integrate human emotions into AI. Now, first of all, is it even possible? Because we can argue and say that that's entirely impossible, because we are biological creatures, right? So we secrete adrenaline, we secrete stress hormone of all kinds and whatnot, and that's why that's what drives our emotion. Emotion is not up here. Emotion is down here. It is actually everywhere. It's a biological response. Okay, and computers don't have hormones, right? They don't have enzymes. They don't have all of these various chemicals, but they can imitate. So what you want to know is neural networks, deep convolution neural nets. So what neural nets do is they learn by observing. They learn by, okay, this is the situation, this is the response. This is the situation, this is the response. And by learning over a long period of time, exposed to many, many samples, they don't need the chemical, but they can imitate how a person would act in a certain situation. In other words, they can imitate an emotional response even though it has quote unquote no emotions, it has no lizard brain that we have, okay? But they can kind of do the same thing. When a person acts in anger, what happens? Things get destroyed, right? Chairs got thrown in the case of a certain Microsoft CEO. Not Bill Gates, the other one. And possibly some people might run into a crowd with firearm or run a car into a crowd, but still we are not talking about a coordinated event. Okay, we're talking about a single person doing something. When an AI has an anger response and has access to a lot of resources, what's going to happen? Very, very bad things. Okay, depending on what the AI has access to, right? If the AI has access to the Uber 18-wheelers, think about that. These 18-wheelers can be transporting fuel. They can be transporting liquefied petroleum gas. And if the AI gets control over these vehicles and go like, you know what, I'm going to drive that thing into a shopping mall. Definitely not a good situation, okay? So, that's why I kind of want you guys to kind of think about these, because some of you may actually end up working with a company, working on AI. So these are the things, it's kind of like ethical stuff that you have to think about before getting into a field. Question?
So I was reading a while back an AI that maintains the schedule of a subway in China. And it makes sure everybody's on time and clocked in and stuff like that, and it keeps track of all of those things, and it gives warnings whenever there's an incident or something like that. And it's like one implication that I was fascinated about, because it could maintain a system that people cannot do that themselves.
Well, there are certain things we cannot do. That's why we got spreadsheets to work on math problems really fast, right? I mean, but the issue with AI is sometimes we cannot predict what the AI is going to do. It can learn, it can change its behavior. Depending on what it learns, that determines how the AI is going to behave in the future. But you're not probably going to be hand-feeding information to train an AI. In other words, you're going to open up the internet and say, okay, AI, go learn stuff by yourself. Then you have no idea what it is going to learn, because the first thing it's going to hit is probably news websites, right? So what do you learn from news articles? Are they good things or bad things about humanity?
Bad.
Usually bad, right? It's not just murder. It has to be the freakiest, the most, sensational kind of, story that get published. So if the AI is only going to watch news articles, it's going to learn from all of these sensational news about bad things happening. So the AI is going to behave like that. You guys have heard about Watson, right? The IBM Watson, the AI engine that played Jeopardy. Jeopardy.
Oh, Jeopardy.
That's Jeopardy. And somebody exposed that thing to the Urban Dictionary. And just read it up, okay? Some of you are smiling because you read that article already. So just look up your Watson Urban Dictionary. Okay, humans created this repository of slang, the Urban Dictionary. Watson could not distinguish between polite language and profanity, which the Urban Dictionary is full of, which is the same thing as news websites. They're filled up with negative stuff. So Watson picked up some bad habits from reading Wikipedia as well, in tests, it even used the word bullshit in an answer to a researcher's query. That's and that's 2013, more than 4 years ago. Okay. So think about that. Okay. And Watson is not fake. Okay. We know Watson is real. Watson was a research project from IBM, and it's able of learning by itself. Depending on what you expose it to, it can learn from all that stuff. So that really kind of helps to show, how unpredictable things can be if you are not controlling what the AI is learning. And most of the time, people don't want to, spoon feed an AI because that's a lot of time, and you want the AI to learn on its own. And when an AI is learning on its own, you have no idea what it is going to learn. I mean, you have watched movies about these things, right? Yep.
I know in the movie Ex Machina, they developed the AI based on Google results. That was a mock company that was Google, I guess. So pretty much all of its intelligence came from Google in general.
Which is reasonable because that's a quick way to locate items. But the way Google prioritizes those search results is based on how we click, right? Because Google at first, okay, so let's say you're looking for something that's relatively common, okay, and Google observes which link we eventually click, and it will use that as part of the data to retrain its engine in order to prioritize what to list first. In other words, the AI is really learning from us based on what we click, what we prefer to click, when we get a Google result. And as a result, the AI is really modeling after humans, as a collective, which I think is not necessarily a good thing. All right. So since so I think we are good with all of these topics, and I'll let Kevin to talk about his debugging bee for a while.
Okay.
Do you have an electronic version of the flyer, or?
An electronic version, yeah.
Okay, so I can pop it up. Is it a PDF?
Yes.
Okay. Here's the file location.
It's going to be called Flyer 2, I believe, because Flyer 1 did not turn out well.
Okay.
Flyer 2 PDF.
Okay.
.pdf, apparently.
All right. Cool.
Okay, so I'm here to tell you guys about the debugging bee we're having. It's put on by the Computer Science Club with help from Mesa, the Design Hub, and the Engineering Club. This is going to be on December 1st. It's a 3-hour event from 12 to 3. We're looking for 8 competitors, and there is a qualifying test you have to take first. We're only taking 8, so it's going to depend on your score on the test. You need to sign up before November 10th. And you need to take the test before November 17th, so you only have a couple weeks. Anyways, we have $100 for first place, so there's a cash reward. There's going to be a drawing at the event for prizes for people who aren't necessarily competing. So if you don't feel like you want to compete but still want to come watch it, feel free. It'll run on December 1st from 12 to 3. And if you want to go ahead and take the qualifying test, if you scroll down, there's a QR code. You'll see the posters. They're all in liberal arts right now. We're in Mesa. Just scan that or go to that Google form link and sign up, and I'll get a hold of you. We're doing the tests in the Computer Science Club from 12 to 3 on Tuesday, Thursdays, or in the Design Hub from 12 to 3 on Fridays.
Am I missing the time here, or is it just not displaying?
It's just not on there. I missed that one, yeah.
Okay.
Someone pointed that out earlier today, too.
Mm-hmm.
We already printed them all up. Not today, though, because you can come in today from 12 to 2, but at 2 we're going to have the Amazon speaker I was talking about last week, so we won't be doing the test at that time. But feel free to stop by for that as well. That'll be in Mesa, actually, today at 2. All right, thank you.
All right, thank you. Oh, yeah, I got it. All right, so getting back to the homework assignment, are there any questions about the homework assignment? It's due on Thursday. So are there any questions about that one? No questions? I'm assuming some of you got it done already. Okay, all right, very good. So for those of you who have not gotten it done, do you have any questions? No? Okay. If there are no questions, we're going to do string compare. Okay, so we'll go ahead and take a look at the C code of string compare, and then we'll convert that into assembly code, and then we'll also find a way to test it too. Did I talk about string compare in this class? Yeah. Yep, I thought so. Okay, so if you want to understand string compare, one way to do it is to just do a man page on string compare. And I think we talked about the C code last time, so we just have to implement the C code in assembly code today. So we'll go to the mouse pad here, and then write it in C first, and strcmp const char p1 as a first pointer, const char p2. So these const are not 100% necessary, but it does make sure that the compiler can make sure that you are not overwriting any content of the strings. Okay. So the basic code is relatively easy. It is really just saying, as long as p1, whatever p1 points to is the same thing as whatever p2 points to, and on top of that, at least one of them is pointing to a non-null value. Continue with the loop. And inside the loop, the only thing we're doing is we're incrementing p1, and we're also incrementing p2. After we exit, we can just say a single return, and what we're returning is p1 minus whatever p1 points to minus whatever p2 points to. That's the string compare function. So the code works because in order to stay in the loop, you're basically relying on these two conditions. The first condition is basically saying these two strings are the same up to this point. Okay, and therefore I cannot distinguish. I cannot tell which one is smaller. But the second condition also makes sure that we are not at the end of the strings, because we need at least one of the strings to be still pointing at a non-null character. But at that time, when you evaluate the right-hand side of the end, the left-hand side has to be true already, which basically means they're both not reaching the end yet. Does that make any sense? Because in order to get to the second or the right-hand side, the conjunction operator is one of the few operators where the order of operation is strictly enforced from left to right. When you're dealing with addition or multiplication, the order can be reversed depending on the mood of the compiler. But when you're dealing with logical and or that type of operator, these two operators, is guaranteed to be from left to right, and it also always uses short-circuited Boolean evaluation. So in order to evaluate whether P1 is pointing to a non-null value or not, it means this condition has to be true already. If this condition is already true and this condition is also true, it means both strings are not ending yet, which is a good reason to keep moving, because we are basically saying it is inconclusive. Everything that we have seen of these two strings are exactly the same, and these strings have not terminated yet. And that's why we stay in the loop. When we get out of the loop, we only have to return this, because according to the string compare description, it returns a negative number if the first string is less than the second string. It returns 0 when both strings are exactly the same, and it returns a positive number when the first string is larger than the second string. This will give us the proper result. Even if the strings do not have the same length, this will still give us the result, because the null character that terminates a string has a value of 0, which is the smallest value possible. Is that okay? All right. So what we'll do is now we'll implement this particular subroutine in assembly. So that begins with string compare as a label. And it always helps to look at the stack to see what is on the stack when this is, when we are getting control as a subroutine. The first thing we see on the stack, or the top part of the stack, would be P2, which is a pointer. Then we see P1, which is another pointer. And then we see the return address. The return address is the one pointed to by register D, which is our stack pointer. So this is guaranteed upon the entry point of a subroutine. Is the parameters are pushed in the reverse order, and the return address is pointed to by, in this case, D, which is our stack pointer. Are there any questions at this point? We can make this assumption because it is the agreement between the caller and the callee. So what we need to do now is to go, okay, can we perform all of these operations using only 3 additional registers? Particularly, can we do the compare using only 3 registers? The answer is, yeah, we can do it that way. It's just going to be a little bit messy because when you have to compare what P2 points to versus what P1 points to, you will need to go through some calculations. But I think we will be fine with only 3 registers. Okay, are there any questions at this point? The original code does not need any local variables, so I'm not going to use any local variables in this case. So I will try to make the assembly code as close to the C code as possible. Okay, so we'll deal with this one first. Okay, we'll retrieve the parameter P1, and we'll retrieve the parameter P2, look at what they point to, and then compare what they point to. All right, so the first one is CPR, okay, copy register, and we'll copy register D to register C. Remember, the first register is the destination, the second one is the source. So if you want to comment, you can always say that C is now the address of the return address. And that's not what we want, okay? Because we want to get to P1, so that means we need an increment C. So at this point, C is going to be the address of P1, not P1 itself, okay? This is the address of P1, which is on the stack. Okay, so we'll go ahead and retrieve P1 at this point. So we use an LD instruction. So we say LD A indirect C, so that, okay, I'm going to put additional spaces here. So at this point, we know A is just P1. Are there any questions about this code at this point? It's all good? Okay. But we are not comparing P1. We want to compare what P1 points to what P2 points to. So we are going to dereference it one more time, but this time we are dereferencing A and put it back into A. So that now A is what P1 points to. So we got the left-hand side of the comparison at this point. Then we'll do the same thing with P2, increment C, because C is still pointing to P1. So after we increment, C now points to P2. Then we do the same trick, except with register C. So the B is now P2. And then we do another dereference with B. So the B is now what P2 points to. Are we still doing okay so far with this code? Still good? Okay. So finally, we can do the compare. So we say CMP AB. Okay, so we compare A and B. There's a trick too. If you don't want to have to do the subtraction later on, we can always do a SUB. Okay, at this point. Okay, so it's a trick, yeah, but it can save you a bunch of code. Okay, but I'm not going to do that because I want to follow this code as closely as possible. Okay. If it is the same, then we have more to check. Because according to the C code here, if they are the same, then we need to check to make sure that P1 is non-null. Okay, so we'll say, check P1 or check D reference P1. Okay, and we'll put the label here. Check D reference P1. We'll put it here. On the other hand, if they are not equal, if A and B, register A and register B do not equal, it's time to jump out. Okay, so we can say terminate the loop. So we'll jump to the end of the entire loop. And here is the end of the entire loop. Okay, so we'll deal with the first label first. The first label says, okay, we know what P1 points to is the same thing as what P2 points to. but we need to check one more thing. We need to make sure that they are not null. Okay, they're not null characters. Yep.
Put a colon at the end of the jump to well there.
Say that one more time.
Do you need the colon at the end at the well?
Oh, we do not need that colon. Thank you, because that would totally mess it up. Okay. All right. So when we are here, we want to check whether A is null or not. Okay. There. Yep.
JZI is just checking for a 0, right?
JCI branches when the result of a calculation is all 0, all the bits are zeros. So in this case, we have a compare, which is the same as a subtraction. So if after subtraction the Z flag is a 1, it means the numbers are the same. It means A and B are the same. We don't know whether they're both zeros or not, but we know they're the same. Okay. So when we are here at check the reference P1, we are just checking A to make sure that it is not 0 itself, okay, to stay in the loop. Or if it is 0, we want to get out of the loop. So at this point, we can do a LDI B0, okay, to force B to be a 0, and then do another comparison. Now, if you don't want to do this because it takes up 2 bytes, that would do the same thing. That would change the content of B to 0. And then we'll do a compare A to B, and then JCI again, but this time when we branch on a Z, or when Z is a 1, it means what P1 is pointing to is null. So that means we should get out of the loop. So we'll go to AND while, or while AND, which is here. So when we get to this point here, it means this is the body, this is the beginning of the body of the loop. In the body of the loop, in the C code, in the body of the loop, all we want to do is to increment P1 and increment P2. They are not in registers. P1 is a parameter on the stack, so is P2. So what we'll do is we'll do something really kind of the same as what we did before. Okay, C is still okay. So if you want to reuse register C at this point, you can, because register C is still pointing to P2 on the stack. So we can now just say LD A from the stack pointer. So the A is now P2. Then we increment A. So A is now P2 plus 1. And then we store it back. So the P2 is P2 plus 1, it's incremented. And then what we do is we decrement C. And after we decrement C, C is now the address of P1. Then we LDA with C, so that C is actually P1. Increment A, so that C is P1 plus 1. And then we do a store back to where C points to, so that P1 on stack is P1 plus 1. Then we can jump back to the beginning of the loop, JMPI, while begin. All right, well, we don't have a while begin label. Yep, go ahead.
Is it LD, AC, is it A equals P1 and A equals P1 this one?
On which line? On this line?
Yeah.
What's this?
Is it supposed to be A equals P1?
Oh, yeah, right, the comment. Yep, you are correct. So this is A as well. Thank you. So are we okay so far with this? So now the question is, where do we put while begin, which is marking the beginning of the entire while loop. So where do you think that should go?
Right after check.
Okay. I can put it all the way up here, right? Now, do we really need to copy D back to C again? Maybe not. So we can probably put the while begin here, at this line, but it doesn't hurt to put it all the way to the beginning, because I don't want to take the risk that I somehow miscalculated C and it's no longer at the beginning of the whole thing. So I'll put while begin all the way back there. Are we still doing okay so far with this code? So far so good? All right. So when we get to while end, we need to implement this code in C, which is kind of messy in a way, because what we need to do is to dereference those two. And by the time we get here, it is possible that we are getting there because one of the pointers is pointing to null, which means I would have destroyed B already. So I cannot just do another SUB, subtract A from B, because B is already a 0. So I cannot make that assumption. Okay, so that means I'm going to have to recalculate everything. So we'll just do the whole thing again. I mean, if we know how to do it the first time, we can now do it a second time. In fact, we can just copy and paste a bunch of code. So we'll just copy and paste everything here and change the very last instruction. So it is not a compare, and this time it is just a subtract SUB, because A is now my return value. So it's all done. So after this, we have the usual return code, which is LD B. I cannot use A again because A is the return value. So we use B to store whatever the stack pointer points to. So the B is the return address. And then we increment the stack pointer. It's very important to remember to increment the stack pointer whenever something is not in use on the stack anymore. Okay. Yep.
Can you use dereference when incrementing? Can you put in a parenthesis?
No. Dereference can only work with LD and ST. So those are the only two instructions. So we're incrementing D, and then we do a JMP B, because this time we want to continue where the return address is. So I think that's our string compare function. Any questions about the string compare function? But are there any questions about the comments? Because I'm trying to document exactly how the whole thing works. Okay, so but this function by itself is not going to be very useful. We cannot test it by itself. So we need the entire program, which starts with the initialization of the stack pointer.
And then create local variables?
Not local. This time I'm going to go for some global variables. So we'll figure out how to do this. So this is main. I'm going to do an LDIA with string 1, decrement D, so that we can push it on the stack. Oh, not push. SDDA, LDIA, string 2, decrement D again, store that onto the stack. So we're pushing the two arguments, and I should probably reverse these two so that we're comparing string 1 to string 2. Remember, when you push the arguments, you have to push it in reverse order. And then we now have the return address, main return address 1, and we'll put the label here, return address 1. Decrement D, because we're pushing it on the stack, store it to where the stack pointer points to, and then we have a JMPI to string compare. And when we return, technically speaking, you should always deallocate the space used up by the parameters. So you always have 2 increment D, and finally we have the halt instruction here. And then at the end of this entire program, we can now perform those two strings or define the two strings. So we have string 1, I did not make the code so they can use actual quotes, and then it will come up with the ASCII code. So we'll have to look up the ASCII table to find out how to spell out something. So man ASCII would give us the ASCII table in Linux. So let's spell out TAK for the first one, TAK. So we have 84, and then we have lowercase a. Lowercase a is 97, and lowercase k, which is 107. But it is also going to be null terminated, so we need a byte of 0 at the end. And in string 2, I'm just going to be lazy here. So it's TAK. We'll add one more byte here. And that's going to be lowercase c, which is 99. Okay, so one is TAK tag, the other one is TACK tag. Okay, are we good? So we'll go ahead and see if this works. All right, so we'll copy and paste from here all the way to the end into the assembler.
It's right there.
Hmm?
It was at the top.
Oh, it's frequently used. Okay. And we just paste. All right. Cool. I also added the tab here. If you look into the tabs, there's a tab right next to source. It's called source debug. And when you look at source debug, it doesn't seem very impressive. But what it does is it shows you the address of each line of code. That can be useful when you're debugging your program because when you track down your PC or the program counter when you're debugging the code, this can help tell you, okay, we're executing this instruction, this is the result. This is when we execute this instruction, this is the result, and so on. Okay. All right. So what we'll do is we're gonna start up the emulator. Okay, so we say java-jar downloads. I'll just say in generic, and then processor w dpc2. Okay, it's the processor. We will download the program first. Go back to here. Go to RAM file. We download the program as string compare, strcmp.csv. Then get back to the simulator, load the program here. Oops. Ah, no. Okay. And string compare, open. And we'll just kind of look at the content. So string compare takes up maybe about 1/4 of all the available bytes. That's including the string too. So that's not too bad, okay? It's not too bad. Right, we get out of here, and then we go to logging, okay? Minimally, okay, when you're debugging a program, minimally you have to track down PC, program counter, okay? Tracking down all the registers can be helpful, okay? But before we do that, I'm gonna do one little thing. You might want to do the same thing to your version of the processor, is to go to the register bank and actually give these things names. So this is register A, this is register B. Oh, I have to change the other file, so it's a little bit too late to do it now. But you might want to label those registers just so that when you look at the trace, it will tell you this is register A instead of just some non-descriptive name of the register. Okay. Okay, so we go to logging again. Let's track down, the registers. So we go to register bank, and you can multi-select if you want to, and add those here. We can also change the radix. Yeah. But that doesn't seem to pop up anything. Oh, okay. So you can change the radix, in here. So you can change it from base 2 to base 16, which is hexadecimal. That can be handy. I like this. Cool. I like. Okay, second thing is we need to track down what's happening on the stack, right? So that's in memory. And we want to track down the last 3 locations for sure. So we look at location 255 all the way back to location 253. But I might want to look up just one more instruction just to make sure that I'm not messing up the stack. Okay, so we'll track all of these and also change the radix of these guys to base 16. Okay. It's just a whole lot easier to read base 16 numbers as opposed to base 2 numbers. It takes up less space as well. And then we can go to file, because if you log it in the table, internal table, it's okay, but it's not, you cannot just save the file and then analyze it later. But if you save it to a file, Okay, string compare.log. That means you can examine the file later on and you can analyze it using a spreadsheet too. So that gives you a lot more ability to debug the program. Okay, close window, and I think we are ready to go. Yes? Okay. So we'll go ahead and take a look at the program counter because that can tell us whether we can stop clocking or not. So Control K start. Okay, so now we are stopping. Okay, first thing first. The program counter reflects 13 in hexadecimal, and now the question is that corresponding to my halt instruction? Or 12, is 12 corresponding to the halt instruction? This is the tab where it becomes useful, and since this is all in binary, so not in hexadecimal, if you want to make it more convenient, you can always do a bin to dec first. Okay. And then from decimal back to hexadecimal. So we have dec to hex after this. So this way it is just a little bit easier to read because we are changing the simulator to display everything in hexadecimal. So now this is column C is a lot more readable compared to column B because it is all in hexadecimal. I'm copy and pasting the whole thing, so in case your program is really long, it will still work. There we go. So back to here, we want to make sure that location 12 has a halt instruction, and it does. So the program does terminate correctly. Does it do the computation correctly? That's the next question. So what we need to do now is to look at the log file. So we can use mousepad to look at the log file. We can use VI. I'm just going to use VI here, string compare.log, and it's a lot easier to read. The header part is kind of difficult to deal with, but I think I can remember what each column is about. So I remember this is the program counter. This is register A, B, C, D, and these correspond to RAM locations. Location 255, 254, 253, and 252. Okay. So the first thing I'm going to check is the last row and see whether, okay, so we're comparing TAK versus TACK, right? So when you look at TAK versus TACK, which one is larger? TAK is string 1, TACK is string 2. So what should string compare return?
Negative.
That's greater, right? Uppercase K, K is greater than C, which means it should return a positive integer in register A. So register A in this case has 08 as a hexadecimal number. So is 08 representing a positive signed value or a negative signed value? We know it's not 0. It's positive. Very good. So the algorithm seems to be doing its job correctly. Second thing, is the stack pointer balanced? In other words, is it going all the way back to where it started off with? Okay, it is 0, 0. It's all good. Did we end up messing up location 252, which should not be modified? Because the entire program should only use 3 locations on the stack. Well, doesn't seem like it, right? We cannot tell if we're overwriting with 0. We cannot tell, but you can see that throughout the execution, it doesn't seem like we are accessing location 252, so we know we are not using the stacking correctly. What else can we tell from here? We can also tell that we are incrementing the 2 pointers, P1 and P2, in the code, because when you look at the time when the subroutine got control, so getting back to here, you can see that the string compare is starting at this location, which is 13 in hexadecimal. Which is okay. 13 is fine because everything is in hexadecimal already. So we can see that this is the entry point. This is the line that corresponds to, okay, we are now in string compare. So at this point, when you go forward, you can see how location 255, which is 3B at this time, and location 254, which is 37 at this point, you can see how they got changed, how they increment over time. Okay, because the loop is supposed to increment these things. So you can see how they go from 373C, 3B to 3C and 3.8. See how it is changed here? Because we are supposed to increment the pointer inside the body of the loop. Right after we increment the loop, we are supposed to go back to the beginning part of the loop here, and that's exactly what we observe as well, because we can see how we got from 2B, which is the end of the entire loop, to 1.3, which is the beginning of the loop. So just by analyzing the trace of the registers of the program counter and also certain locations on the stack, you can really see how the program executed. And if I do have a bug in this program, this is how I'm gonna have. This is what I would do to find out where the bug is, because I can track backwards. This column here, the first column, which is corresponding to the program counter, this column here can now be corresponded to this table here, because I put the hexadecimal version of the address right next to the source code. So that makes it very easy to tell, oh, okay, we are here, we're here, we're here. Oh, it's not supposed to get here. Then you know that the program is doing something wrong. But you can also look at the value of the registers and say, okay, is this register supposed to have this particular value at this time? If not, then we know where the bug is. Or at least we know the bug has already occurred. Then you have to track backwards to find out why it happened. Are we doing okay so far with this code and also the process of debugging your code? Any questions? Anything else that you might want to do with this code? I mean, with the assembler to help you debug the program? Hook it up to an AI. Sophia, can you help me debug the program? And Sophia is going to say, go ask Han. Han is going to ask for your social security number and your credit card number, so that he can buy enough equipment to create a singularity. But are there any questions about this entire session? Because what I'm trying to do is to illustrate several things. One is how to convert C code into assembly code. Two is how we use the stack, okay? Where the parameters are located at, and how we convert C code into assembly code without changing the nature of the code itself. And three is how do we debug a program, okay? Because there's no printf in this entire thing. So without any printf, there's no GDB either. How do you debug a program? You have to trace it. You have to use the simulator's ability to track down the values in RAM, the values of the registers, the value of the program counter, so that you can track it down and go like, but you have to have an idea of, okay, at this point, I think the value of this register should be blah, blah, blah. Or I should be able to, I should take this branch, I should take that branch, I should get out of the loop, and so on. So when the program behaves unexpectedly, then you know there's a problem. It is very tedious. There's no sugar coating of that part. Any questions at all? No questions? Yep, go ahead.
Can you explain the main return address one again?
The main return address, you mean this one?
Yeah.
So the main return address is at location 10. So that means what this line of code is going to do is register A will now have a value of 10 in hexadecimal. It is called the return address because it is now pushed on the stack. Because the next line is decrementing the stack pointer, and then we are storing that 10 on stack, which is observable when you look at the trace, because when you look at the trace, you can see how this 10 is at that location. So at this point of the stack, we have string 2, we have string 1, and then we have the return address. Is that okay? Yeah. So the return address is pointed to by the stack pointer when you're at the end of the subroutine. In other words, by the time you get to this line here, which is at the end of the subroutine, the stack pointer should still be pointing at the return address, which means we put the 10 back to register B in this case, and then we increment the stack pointer because that byte is now used already, so we can deallocate it from the stack. And then on line 59, this is really just copying register B to the program counter. Okay, since program counter is now 10, that means the next location we execute will now be location 10. But where's location 10? Location 10 is right here. This is location 10, which is the continuation in the caller after the call to the subroutine. So this is the whole mechanism of calling and returning. Are there any questions? Yep.
So register key is always pointing to return address?
At the entry point of a subroutine, yes. And it should still point to the return address at the end of a subroutine. But in between, if you push something on the stack, you call some other subroutines, and you forget to deallocate, the parameters, then the stack pointer may point to something other than the return address, which means your program will still attempt the return, but it's going to use the wrong address to return to, and that will be something that you have to watch out for. Is okay, I'm returning, but is it going back to where it's supposed to? So when you're debugging your program, especially with a homework assignment, when you're debugging your program, whenever you go from the end of a subroutine, which you cannot change, okay, so track down this location in the trace. Every time you go to every time your program counter becomes 37 in hexadecimal, find out where it goes to continue execution, and make sure that it goes to a particular label to continue execution. If it does not, that means you somehow did not balance the stack pointer correctly, and it's using the wrong byte on the stack as a return address. So in this case, we know 37 is the return, which means in the trace, we are looking for 37 as the PC, as the program counter, and okay, that's 37 right here. So 37 is right here, which means the next location, which is 10 in this case, should correspond to a return continuation point, which in this case it worked correctly because I didn't mess up the stack. But it returns to like 14, okay, then I know I have a problem because it is not returning to a designated return point. So this is a trick that you might want to use when you're debugging your program, is to watch out for these particular issues. All right, any questions? Any questions? Okay. We've got about 10 minutes. So I have to train you guys to basically counter the future evil AIs, which means I want to turn you guys into hackers, okay? All right, so this is something that hackers have to deal with. So typically a hacker can get access to this, okay? Because this stuff has to live in the memory of the computer that is executing the program. So you can always get a RAM dump of a program that is in execution. Okay, there's no question about that. So the next question is, from here, how do you decipher this program and figure out what the program does? So let's say somebody said, okay, my computer is hacked, okay? But fortunately, because I'm running this particular server as a virtual machine, I was able to get a RAM dump, after it was hacked. And you're going to reverse engineer how the hack happened, what happened to that particular program, and what is the payload of the virus or worm that causes all kinds of problems. Okay, so you're given this. So what do you do next?
joke. I was gonna say click close limit.
Well, send it to Sophia.
To find out what like values represent what instructions, right?
Right. So exactly. So these are all opcodes. You know the program starts execution at location 0. Okay, that's given. Provided that this is our simulator, and it always starts a program at location 0. So you go like, okay, so let me figure out what is 6F. Okay. So the long way of doing this is to go to the spreadsheet, go to the mnemonic table, and then you look up what is 6F. So 6F is, there's no code here corresponding to 6F. The closest one is 6C. And in the case of 6C, it is an LDI instruction. And the reason why you're seeing 6F instead of 6C is because 2 bits of 6C specifies which register is the one getting modified. Okay? And that turns out to be the least significant 2 bits. So that's why you get 6F. Because 6C with the least significant 2 bits turned on is 6F. So now you know it is an LDI instruction with register D as a destination. Then you switch back to the RAM dump here. Yep.
How do you know it was registered D? Because of the...
Huh?
Oh, right. I think I got
Yeah,
it.
there are 2 places where it is described. That's one. But you know the next byte specifies what you put into the register. So by looking at 6F00, you know it's LDI D and then 0. And then you know this one is LDI A with 3B. And then this is EF is a decrement D. Okay. And F3 is store to register, store to what D points to from register A, and so on. So you will have to kind of decode this. This is really tedious. You don't want to do it this way. So what you do is you write a disassembler. If none exists, if one is already there, you use a disassembler. So the result of a disassembler, applying the disassembler, is you get back to this. So basically, the disassembler allows you to go from the object code, which is what you see in RAM, going back to somewhat readable code in this format. That's the disassembler. So after you get the disassembled code from a particular memory dump, what do you do next? You convert it back into C code. Okay? So now the question is, how do we convert it back to C code? Well, knowing that this code is probably compiled, it has certain signatures, okay? So the first thing you look for are the jumps, okay? The jumps are far more important than everything else. Because the jumps, will tell you about the control structure of a program. And as a result, that tells you about the logic of the program. The rest is really just, which memory location we are accessing. So in this case, when you look at this code here, we look at all the jump instructions. This is a jump instruction, this is a jump instruction, this is a jump instruction, this is a jump instruction. When you're locating loops, loops are always signified by a jump going back to a label that is earlier. Okay? When you're looking for a conditional statement, it is always, a code, a jump that jumps around a block of code, okay? And that's making it conditional. If you're looking at a conditional branch that has both the then and the else, then you're looking for the format that looks like this. So you're looking for some code, it has a conditional branch, you're looking at another block of code, and there's an unconditional branch here to jump around another block of code. So there's a conditional branch here to jump here, and then this is the actual end of the entire if-then-else statement. So you're looking for structures like this to reverse engineer the code from assembly code back to high-level code, which is C code in this case. Okay? So once you have the structure, then you look at how memory is accessed. Now that is a little bit tedious with a toy processor because we have very few registers and we have very few instructions, so the calculation of what we are accessing can be a little bit tedious. But the focus in those cases, if you want to focus on what instructions are accessing memory locations, you are basically looking at something like this. It is always going to be an indirect access with parentheses. because all the local variables and all the parameters live in RAM. And the only way you can get something from RAM to do any type of processing is to put it into register. In other words, you first locate the actual useful instructions like CMP, add, subtract, that sort of thing, and then you go back and ask the question, how did we get that register B to be prepared for compare? Then you track your way backwards so that you can figure out, oh, okay, I see we are comparing this byte on the stack to that byte on the stack, or what that byte is pointing to, and stuff like that. So that's basically how you reverse engineer the entire thing. It's also called decompiling a program, okay, which is the reverse of compiling a program. After you decompile a program, what do? You're a hacker, remember. Hack them back.
Yep. You can alter the RAM to do what you want, right?
You can alter the RAM, okay. Go ahead.
You can change the instruction and recompile it.
You can potentially do that. It depends on what you're trying to accomplish, right? So, what do you think, as a hacker, what would be some of your objectives?
Information, like security.
Okay. Information, security.
Hide yourself. Hide your program in the computer.
You can learn. You can try to learn how to program.
No, it's in the computer. Hide itself to not be detected by antivirus.
Okay, so how the virus hide itself from the virus scanners?
Yeah, you can see how the program converts passwords, how it encrypts stuff and hashes stuff, and the developer will get it backwards.
And how it handles the information.
Reverse it. Steal the passwords and stuff.
Or open a shell.
Yeah.
Open a shell and have it so that you have a backdoor so that you can gain remote access to that particular computer. Yep, go ahead.
I was thinking the overload the memory or something like that.
Stack, it's called a stack overflow exploit. Yep. Now, stack overflow exploit is very interesting. I don't have enough time today to set up the experiment, but if you can do stack overflow exploit, you can make a program do things that it is not supposed to. But it takes some experimentation to find out, at which point it is stack overflowing, and then you have to determine how should I overflow the stack, what stuff should I overflow it with in order to make it do certain things. But all of that requires you to be able to analyze the disassembled code so they can figure out which part is accessing the stack. For instance, in this case, the vulnerability is coming from this jump here. Because this jump instruction is based on something on the stack. If I can somehow overflow the stack so that I have actual control over whatever the stack pointer is pointing to at this point, then I can alter the path of the execution of this program arbitrarily to my liking. Okay? So that is the kind of stuff that you're dealing with. Okay? Any questions? All right, so we got 2 minutes left. I'm going to give you a picture. Just to relate to what we have discussed already and how Stack Overflow exploits work. So we know the stack has parameters first. Okay? So this is param 3, param 2, param 1, right? Okay, because we push the parameters. The caller is supposed to do this. And then we have the return address. The proper return address is supposed to be here. And then if the subroutine has any local variables, it's going to be below the return address. So now we have all the local variables. Is that okay? High memory address, low memory address. Your local variables may contain arrays. Okay, so let's say you have an array here. So we are looking at things from the C perspective. So this is an array, we call it array A. Array A has a proper beginning, and it has got 1, 2, 3, 4, 5 elements. So element 4 is supposed to be the end of array A. Unfortunately, if somebody decides, you know what, I'm going to use string copy and not string and copy, then it depends on when the source string is ending, then it will stop the copying. If the source string has a lot more bytes before the no character, then it will overwrite these 5 locations, which are proper. They're really a part of A. But when the source string has more bytes, it will start to overwrite other things. In other words, it will start to overwrite other local variables. Eventually, what do you think is going to overwrite? The return address. So when the return address is overwritten and your function returns, it will go back to this location because this is still, supposedly D would still be pointing back to here at the end of the subroutine. So now whatever you put here is the location that your program will continue execution. You can now steer your program to go to wherever place you want it to go. So that's, in a nutshell, this is how Stack Overflow exploits work. At least one form of Stack Overflow exploit. So the next question is, how do we find problems like this? Because it seems like we are relying on some iffy practice of coding, right? Instead of using string and copy, somebody chose to use string copy because it's easier. I don't have to pass one more parameter. So how do you find those things? Well, string and copy versus string copy is a call to a library subroutine, okay? In other words, there are probably ways for you to look at the binary code of a program and find out whether it's calling string copy itself as opposed to string and copy. So this is from the perspective of actually looking at the source code to find out what problems it might have. Another problem, or another way to look at this, is to look at the original purpose of this program. So let's say this program originally is supposed to process a particular file that has a specific file format. A particular field of that file says, okay, this field is supposed to have only 5 bytes, including the no character. Okay, so if everybody plays by the rule, that field will only have up to 5 characters, including the no character, the no terminator. So what a hacker does, okay, and this is what it takes to become a hacker, is to question everything. Is to say, what if I don't play by this rule? Okay, so you intentionally make a file that violates that particular specification and say, I know I'm supposed to only have 5 characters here. I'm going to make it 50 and see what happens. Okay, if the program checks and go like invalid, kick it out. Okay, cool, no problem. If the program crashes because it overwrites the return address to some random location and it cannot really continue execution at that point, it's going to crash. But the crashing is telling you a clue. Okay, it's telling the hacker a clue and say, maybe I can control how it crashes. And that's when you look into, that's when you use GDB, when you test run the program with specifically formatted input so that you can control how it crashes. And when it does crash, you use GDB to look at the stack. You use GDB to look at the program counter. And you use GDB to analyze how memory is laid out until you figure out how to change exactly this location so that you have control over where it continues execution. That's how some of the hacking is done. Okay, there are all kinds of hacking, okay, but when you're in a computer science program, this is the kind of hacking that I want you guys to learn. SQL injection is yet another really popular type of hacking that can hack into websites, but that's more appropriate for a web scripting class. This is much more appropriate for a class like you guys, people who have learned C and C++ programming and are getting into assembly language programming, because it is all relevant to what you're learning. So are we doing okay so far with this? Sort of? So maybe at the end of the semester, the challenge to get your grade is to hack into the server and change your own grade. I think that was one computer security class was actually graded that way. Of course, in that case, the professor intentionally planted vulnerabilities in the server so that it's actually doable. I wouldn't do it to Canvas. Okay, if you get arrested and sent to jail, I'm not liable. Because they track everything. They track all the suspicious traffic and so on and so forth. All right. Well, we are running out of time today, and I will go to the lab. For those of you who are continuing to do your homework, we can go to the lab and I can answer questions over there.